and welcome to Kings of Curiosity. I'm your host, Gillian Tett, and I serve as the 45th Provost of King's College. I took the role here to help champion the next generation of students and researchers, because I believe that our thinkers, scientists, artists, and writers are national treasures, and they're a huge resource, and we should be celebrating them, supporting them, and yes, of course, funding them too, if we want to create a better future. Now, we all know that the British government has set pretty ambitious net zero targets, and globally there's a target for aviation sector to reach net zero by 2050, which sounds a long way off, but actually it's not. So we're curious to find out about how exactly engineers are working to make this happen and whether it really can be realistic as a goal or not. And today we're speaking to two engineering professors, Nick Atkins and Chez, who are working on net zero aviation, and in particular, how to design planes to support sustainable flying, and how that has links unexpectedly to Olympic cycling and King Charles. So Nick and Chez, it's great to see you here today. Thanks for coming along. And I know you're both working on sustainable aviation at the Whittle Lab, which is named, of course, after Frank Whittle, who is one of Cambridge's great heroes who's not terribly well known. Chez, tell us very briefly who Frank Whittle was.
So Frank Whittle was the British inventor of the jet engine, and he came up with the patent for the first jet engine in the 1930s, actually when he was in Cambridge, I think.
Wow. And of course, he then went on to play an incredibly important role in World War II, and so should be much better known. But so what you're both working on is sustainable aviation, and you've just come out with a report from the Whittle Lab about the key steps needed to create sustainable aviation. And I think there are 4 of them, aren't there?
Yeah, that's right. So firstly, it's worth saying that aviation currently contributes just a few percent of the total contribution of emissions to global warming. But one of the other aspects that's unique to aviation, really, is that there's not just about carbon dioxide. There's non-carbon emissions from aircraft. So in particular, there's nitrous oxides that are emitted at high altitude that contribute to global warming. But perhaps most importantly, there are contrails.
Contrails, and what are they?
So contrails are, if you imagine you're looking up on a sunny day, clear blue sky, you sometimes see a trail left behind the aircraft. And this is a trail of ice crystals, and these contrails can be persistent. And if they're persistent, they then go on to form contrail cirrus, and this contributes to global warming overall.
So those are those white streaks we see. So that's one problem, the contrails. Tell us about the other 3 key issues.
Yeah, so as I say, the contrails could be 50% of the total problem. And so the first area of focus that the report from the Aviation Impact Accelerator at the Whittle Lab has seen is to develop ways of avoiding contrail formation. The other 3 points are firstly is changing the fuel that we fly with. So currently we use kerosene, which is of course from oil, and we want to move to sustainable aviation fuels. So fuels sourced using renewable electricity and either combining carbon from the atmosphere with hydrogen or using hydrogen as a fuel.
So that's a bit like putting sort of, lead-free petrol in your car. It suddenly means that you're still driving the car, but you've got much better fuel behind it.
Yeah, absolutely. So then the other area is improvements in the system efficiency. So currently when you fly in an aircraft, particularly say you fly on a short-haul flight from London to Edinburgh, say, the aircraft you're flying was probably designed for flights that are much larger, so flights from London to, say, North Africa or further. And you're using an aircraft in a range it wasn't designed for, and a lot of the time without the number of passengers that it was designed for. So it ends up being much higher fuel burn per passenger kilometre. So we can improve the system efficiency by matching the aircraft better to the flight, but that would need change in the fleet, because at the moment airlines like to just use the same aircraft across all their flights. But the last area that's identified in the report, and this is the area that is the focus of mine and Nick's research, are radical new technologies to reduce the energy use of aircraft on board and to improve their efficiency.
So what kind of engineers are you exactly? How do you describe yourself within that kind of moonshot world where you're trying to change the way that planes actually fly? Tell me, Chez.
So my area is looking at new propulsion technologies and ways in particular of how we package the aircraft engines with the airframe. So at the moment, you have podded engines below the wing, so the engine is quite separate from the aircraft. And we've already achieved a lot of the easy wins, if you like, of improving efficiency. Engineers have been working for 60 years, reducing engine fuel burn. So now to make significant new improvements, reducing fuel burn and energy use, we want to package the engines differently with the airframe. And it's those different integrations of engine and airframe that I'm looking at.
Fascinating. And what about you, Nick? What are you looking at?
So my main sort of area of research at the moment is trying to work out how we can test these sort of aerothermal ideas much quicker. So with the sort of fluid mechanics and sort of heat transfer that we do, we still can't use computer models just to sort of get the right answer. So we use a combination of testing and numerical modeling. So traditionally that might take 10 years to get a PhD level idea through to sort of a big verification test, as we call it, and to tackle this kind of push to get net zero aviation or sustainable aviation in a sort of short sort of decade type timescale, we need to really speed that up.
Right.
But to get these big drops in fuel consumption that Chez was talking about, we need to change the architecture of the plane.
And that's actually, as I understand it, you're trying, because I went up and saw your Whittle lab, and there was a bicycle display on the side. And I thought, well, we're looking at planes, we're not looking at bicycles. But tell us why the bicycles are so important and the hidden link with the Olympics, because I think this is something that we should all be really proud of.
So a while ago, it was a fantastic scheme from the Royal Academy of Engineering, and they funded 3 innovation professors, one of which was a guy called Tony Pennell, who was heading up the technology side of the UK cycling team. And we used to run lots of master's projects, so 4th-year undergraduates. And from some of my gas turbine research, where we were looking at the state of the flow on the blades with infrared cameras, we could look at the state of the flow on cyclist bodies in the wind tunnel.
What, you mean all the people who go into the Olympic races and stuff like that?
Yeah.
So you were actually using your students to help the British cycling team win medals.
So we tested out the ideas in the wind tunnels for the sort of projects, and then we went and did it for real at the UK cycling tunnel down in Southampton.
Wow. And what kind of impact did you have? I bet your students must have loved that, didn't they?
So it was a real kind of stroke of luck where we found that we could tune the roughness of the suits to world record pace. So the way you have the little dimples on golf balls makes them go faster. So it just so happens that the speed of track cycling is right at the point where you can actually tune the drag of the cyclist quite dramatically by changing the roughness.
Wow.
So it's analogous to the dimples, but we put perfect world records pace dimples on the suits.
This is why I love talking to engineers, because, you know, you guys are doing practical stuff that everyone can actually relate to immediately and understand. So, you know, whether it's golf balls or cycling or planes and things like that, it's just so inspiring to hear how you're taking ideas and turning them into practice. But so you took this sort of experience of basically streamlining cycling costumes to make them go faster. And you're basically doing the same thing roughly for planes, as I understand it. Is that a very crude, non-scientist way of explaining?
So the trouble, when you test things in a wind tunnel, we can't test the full realistic conditions. So we have to make compromises so that we can go fast. And one of the things you have to be careful of is what we call the state of the boundary layer. So the flow is either nice and smooth as it goes over the surfaces, or it becomes turbulent and chaotic. And there's roughly a factor of 3 difference in the drag. And if you don't know what's happening on all the surfaces of your experiments, you can get very confusing results. And it's one of the reasons why people go for these big, expensive tests. So being able to sort of see the boundary layer is a sort of unlock in terms of speed.
But yeah, one thing I was going to say is sort of what's a real central part of the Whittle Lab is being at the forefront of both experimental methods and computational methods. And Nick's infrared camera technique is something that's really at the forefront of the experimental methods. And the projects we do at the Whittle have always been combining experiments with computational methods and kind of understanding the fundamental physics to then solve a problem with industry that's really relevant. And it's always been at the sort of forefront of these techniques, which has enabled us to get to the bottom of what's happening in the physics.
Right. So it's having all the brainiac theory, but then actually putting it into practice quickly, effectively.
Yeah.
And tell us what the infrared camera thing is, because that sounds a bit James Bond-like.
So you want to be able to see what's happening to the... So the thing with a fluid is you have it in a wind tunnel. So when we say fluid, we generally mean air in our wind tunnels. You can't see it. So you've got to stick something in it to measure what it's doing. And when we look at the surfaces, we can actually use a little bit of heat through the surface to see whether the flow near the surface is smooth or turbulent. So this kind of switching boundary layer state that I was talking about. It's a simple thing, really. We worked out if you tune the thickness of a little insulator on the surface, so you put a little coating, maybe some plastic or some rapid prototyping, or even just a film. If you get that the right thickness, the signal to noise ratio of the experiment, you can make it really nice and high and simple and easy. So people have been trying this technique, but it's one of our undergraduate interview questions. So
right, you mean you ask them how they can imagine it?
Well, it's an analogy with electrical resistors. So if you've got a battery and a resistor, to get the most power out of the battery, the load has to have the same resistance as the battery, and it's one of the questions that we often set at interview.
Well, if any undergraduates who want to be applicants
spoilt it now.
Are wanting to apply to Cambridge, you now spoilt it. But that leads me to a question then, which is, both of you, what inspired you to get into this field in the first place? I mean, tell us, Chez, did you grow up thinking, I want to make planes go faster?
So, not particularly. I came wanting to do engineering as an undergraduate at admissions, but then I was supervised, particularly by the fellows at King's, and there was one fellow in particular in thermodynamics, Professor Young, and I was thinking if I was going to go into electrical engineering, and the great thing about the Tripos here is you can switch the branch of engineering, and he was so inspiring in thermodynamics and fluids that I went in that direction. And the other thing was with the connection with the Whittle Lab, where I was working as an undergraduate in my fourth year, there was the partnership with industry, Rolls-Royce, and I went to work in Rolls-Royce for a while, and then there was an opportunity of doing a PhD with them, and I came back and managed to do a PhD with Rolls-Royce, and then I became a postdoc working on a project called the Silent Aircraft Initiative, and there we were focused on reducing noise from aircraft. But in doing that project, we then realized that, it's actually going to be greenhouse gas emissions from aircraft that are going to be important. And this was back in sort of 2003, 2004.
Amazing. It really illustrates a point I often tell students, which is you have to be open to colliding with the unexpected. And you never know. You start off thinking, I only want to study X, and you suddenly collide with people and ideas and experiences you never dreamt of that take you in new directions. But what about you, Nick? How did you get into this?
So it was a similar story. I think I grew up wanting to be an engineer. I think I wanted to design cars.
Were you one of those kids with big Lego sets and stuff like that?
Yeah, I think there's lots of Lego. But I had a similar thing. So I had a fluid mechanics supervisor who was incredibly inspiring. And then that led on to an undergraduate fourth-year master's project in the Oxford lab that does similar work to the Whittle Laboratory. And it just sort of took off from there with a PhD and a junior research fellowship in sort of testing aerodynamics. So.
And I understand that James Taylor, the other person, was also part of your student body, and then you sort of decided that he was so brilliant that you were going to hire him.
Exactly. Well, my claim to fame is that I interviewed him alongside John Young for admissions, and we identified that spark that he had. I remember bringing along a portfolio of something he'd done with remote-controlled aircraft, and it was just incredibly impressive for a 17-year-old at the time. And James has just been on a trajectory. He's made an incredible impact on the Whittle Lab and completely transformed how we do some of the projects.
I must say, one of the things I love about the Whittle Lab is the fact you've got people with very different skill sets. And so some are more comfortable doing all the brainiac stuff, with a computer, and some of you are more practical in terms of actually, turning it into different types of operations and things. And so it's a really exciting team. And of course, there's another aspect to it, which we're very interested in because we're sitting in King's College, which is that King Charles has got interested in the Whittle Lab as well. Do we know why?
So I think one of the key aspects that King Charles sees in the Whittle Lab is our, in many ways, close connection with industry. So we try to work on the sort of good science, but asking the right questions by being close to industry. So that enables us the chance to have impact and be ambitious with having impact in the actual sort of change in the aircraft. I think he's very keen to see some action. He's been thinking about these issues for a long time. And so a laboratory that wants to actually make change.
So he really wants to see practical examples of British innovation turning into real solutions, rather than just assuming that they all come out of Silicon Valley or somewhere else like that.
Yeah, I think that's absolutely right. And the other thing to say is that the aviation sector is quite siloed insofar as the aircraft designed separately from the engines, and then the airlines operate independently. There's the air traffic control, which is separate as well. And the King is a great convener, and he's brought the different parties together. But also he saw the Whittle Lab through the Aviation Impact Accelerator as a way of tackling this multidisciplinary problem. And we've brought in people from all different disciplines to look at this.
Tell us, Chez, about the partnership with industry, because I understand you've got a couple of partners, don't you?
Yeah, so we've actually got several industry partners, and that partnership with industry is really core to what we do in the Whittle Laboratory. We're a university technology centre and have been with Rolls-Royce since 1989, and we're now a technology centre for Mitsubishi Heavy Industries, and they invested in an extension of our lab in the early 2000s.
And Siemens UK, long partnership, working with them on the energy side.
So it really is very international then.
Yeah, and we're bringing in, working with other companies such as Boeing. We've worked with Dyson and others as well. And so partly that brings us the real industry relevance of the research, but also our research has had a great record of having impact on industry. So industry have taken changes in the designs that we've explored, or techniques on the design, and brought that, that's now flying on aircraft. But also some of the methods that we've developed, industry then have taken on these methods and they use those as part of their design process.
And so we've had these long established sort of relationships with the sort of maybe traditional players in the propulsion and power sort of sectors. But one of the things about getting this kind of radical change that we're interested in is allowing access to the sort of research we do to startups and SMEs. So over the last sort of 4 or 5 years, we've been pushing our work with smaller companies. For example, with electric flight, there's a wonderful consortium that James Taylor, one of the King's Fellows, has been working with. And having these 10-year programs isn't accessible to startups. It just doesn't fit. It just doesn't work. So accelerating and reducing the sort of the price of entry to testing is key to allowing these startups to sort of access the sort of research that we do.
That's fascinating because, of course, Cambridge has got a very dense ecosystem of startups, and the university and King's College are now putting a lot of effort into trying to encourage more startups and more entrepreneurship. So, a lot of people say right now that actually the whole green reform movement is going backwards. I was at the UN General Assembly in the Climate Week, and there was a lot of despondency amongst the green activists about some of the political backlash to the reforms. So people might be asking, how confident are you that you can actually keep pressing ahead with this? Is it going to actually really contribute to net zero targets?
So I think, as Nick mentioned before, we need to move faster, and we need to have the things in place to help us move faster, whether that's through government policy and other aspects. But I do think this issue is not going to go away. And, there will be times when it becomes to the sort of the front of the agenda or kind of recedes a little bit. I think in the longer term, we're going to continue working at this. And we see there are technical solutions and, great areas of research to work on in order to achieve net zero. And this is, it's a long-term thing, even if, we're aiming for 2050, which isn't really that far away in terms of timescales for aviation, but we've got to work at this. It's really
because that's the
intensely to get there.
official target, isn't it, for the UK and elsewhere, is to try and get aviation to net zero by 2050, which, as you say, sounds like it's a long way away, but actually it's coming closer. And of course, with 2030, the UK government set other targets as well, which are at risk of being rolled back. But Nick, from your perspective, how soon do you think we'll be able to turn any of these ideas into meaningful improvements?
So, in the past, aeroplanes and new engines have developed very quickly. So you can put small teams together, the right teams, and you can have very rapid progress when there's some sort of imperative.
Well, we saw that, of course, in World War II with Frank Whittle, didn't they? Because when they're in the middle of the war, they had to design, was it Spitfires or whatever they had to do very fast?
And even going back to the beginning of steam turbines powering ships, it was seen it just wasn't possible. You can't do this. And then the first sort of turbine-powered ship was sort of developed in opposition to the sort of views of the establishment, and it turned up at a naval exhibition, and shot past all the existing things. And then within 10 years, everything had changed.
So sometimes you can have these brilliant ideas that change things incredibly fast.
And it was the same with Frank Whittle. He was told, stop messing around with these. It'll never fly. It'll never work. It'll never work. So, the original Whittle turbine engines were developed in sort of opposition to the received knowledge of the establishment. And even at the end, when they got the first gas turbine planes flying, one of the key engineers, a Cambridge engineer called Bob Fielden, he said, I think this might work for land-based power. And I think it's probably all slightly inaccurate, but even Whittle said, it'll never work for land-based power. And one of the biggest decarbonisations has been moving from coal to combined cycle gas-fired power stations, which are driven by the exact technology from the aviation gas turbines. So the idea that things can't change is fairly standard.
We need imagination.
Yeah, no, I was just going to add to that a lot of senior people in aerospace didn't believe in Frank Whittle's idea at the time, and they thought an engine to power a plane had to have a propeller. And I think even the prototype, when they fitted it up for the first test flight, they had to fit a dummy propeller to the front to fool people. And they never believed it until it actually flew. And it was when Frank Whittle was at Cambridge that he foresaw everything that was going to really happen with jet engine development. He saw that we'd get to high temperature materials, and that we'd ultimately go to with these much larger engines that we've got. If you look at in the front of a jet engine on aircraft now, it's huge diameter, and that's in order to get very efficient propulsion of the aircraft. But also he saw that was what was needed to fly fast and high and efficiently over long distances.
So, dear listener, if you're listening to this and think that it's impossible to imagine a world without contrails or streamlined planes, just think back to Frank Whittle and how everyone laughed when he said that a plane could have a jet engine without a propeller. It shows it can be done.
Exactly.
But just going back to the 4 points at the beginning. So the third one, moving to the sustainable fuels, that's really key because there is no silver bullet for long-haul flight. So we can divide flight up into maybe, let's say, 3 different sort of sections. We've got very short haul, so let's call it flying taxis or flying cars. The technology's there. There's many startups working on it. Some of them are coming, some of them are going. But that will be a reality in some form, very, very soon. The middle haul or sort of regional aircraft, it all gets very complicated. There's lots of options. Most of that can be replaced by train travel. So, that's probably the right way to go. So when we're talking about sustainable flight, we're really talking about solving the thorny problem of long-haul flight. So just to put it in perspective, up to 40% of the takeoff weight of a long-haul flight aircraft is fuel. So
wow.
that's
So
the
if you've
problem
cut
that needs solving. So in answer to your previous question about, with the change in sort of ideas about how fast we need to go for decarbonisation, all of the things that we're talking about in terms of the technology, they save fuel to make the change of fuel easier. So as the fashions come and go in terms of big action at the sort of, European or global level, we can just sort of work away in the background, reducing the fuel consumption. As the fashions change, the problem just gets easier and easier to make the big decisions where we actually change the fuel. Hydrogen fuel, liquid hydrogen is a bit of a bigger leap, but there's more gains to come. So that's where we're talking about the ambition. So we're actually working on thinking about the benefits we can get from running liquid hydrogen in engines.
Yeah, so if you move to liquid hydrogen, hydrogen has more energy per kilogram, but it has a lot more volume per megajoule of energy. So to take hydrogen onto an aircraft, you've got to liquefy it, and the huge advantage, of course, is there's no carbon in hydrogen, but you've got to store it at these very low temperatures. You have to change the infrastructure as well as change the aircraft, and you're going to have these much larger tanks, probably spherical tanks, and they'll take up a lot of space in the fuselage. So one thing I'm working on, which relates actually back to Nick's boundary layer measurements on the cyclist, is a technology called boundary layer ingestion. And the idea there is, rather than having your engine separate from the aircraft, say on a pod below the wing, you put a propulsor at the back of the fuselage. And so all of the boundary layer, or the slow-moving flow over the fuselage, which causes the aircraft drag, you take into that rear propulsor and you re-energize it and turn it into thrust. And that means you end up with much more efficient propulsion. But there's more of a need for things like that when you move to hydrogen, because you've got these bigger, say, fuselages, more drag that you need to deal with. So we're trying to combine where there's sort of these technological unlocks, perhaps using hydrogen with something like this boundary layer ingestion propulsion.
I must say, one of the things I've learned about being in Cambridge is if I ever feel tempted to get too depressed about the state of the world, I need to go and either spend time in a lab and look at the amazing innovations that are coming through, because we really are living in a golden age of science right now. And just talk to some of the people doing this, because the gleam in your eyes when you talk with so much passion about, the hydrogen, about the wind tunnels and stuff, it's just amazing. I mean, it's so inspiring to know there are people who really think that you can actually change the world with this stuff.
Yeah, I mean, it's really, really fun getting involved in these, and it's some of the time it's part our hobby as well as our profession. We want doing these tests, and the amazing thing in Cambridge is that you have such talent coming through of young people who can turn their hand to these problems and have new ideas.
So that's where the sort of, in many ways, the college comes in. So the sort of contact with the undergraduates coming through in the supervisions really does kind of help you think in a good way. So
the fact you're forced to sit down with a bunch of people asking you why, makes you actually articulate it in your own mind and test your own ideas out.
I think it's, for me, it's through my career, it's been absolutely essential.
I mean, I always think that, the Cambridge colleges are a bit like chemistry experiments, and you take all these bright molecules from all over the world, shove them together, put them under high pressure, and they all collide and create new compounds and ideas.
Yeah, absolutely. And in this case of aviation, it is very multidisciplinary. So, I mean, whether you're studying chemistry, geography, or economics, there's a contribution to be made to achieving sort of net zero for aviation.
Are you using AI in developing these moonshots? And I ask that because I know that AI has really changed the way that life science is doing its research. Can you do that for aviation, sustainable aviation as well?
Yeah, I think that's really important. We need to be at the forefront of using AI for understanding the flow fields we're looking at and to developing new designs. And James Taylor, the other fellow in engineering, is really someone you should, could talk to on this. But what he has done is he had a project combining someone from industry in design, someone in machine learning, and himself, and they were using machine learning to guide them in what experiments they needed to do to understand how to improve the compressor of a jet engine.
That's fascinating. And James is a fellow at King's as well and is very engaged in the team. And it shows how you're using different skill sets to really come together and test out different types of approaches and ideas.
Absolutely. And I think there's going to be more use of AI in our field in particular. We're trying to train some AI clients at the moment. I think this is right, Nick, in terms of being sort of trained up in the Whittle Lab way of thinking with all the Whittle Lab literature so that we can use them for developing designs of jet engine components.
So you can have agentic AI tools that basically potentially help you, or you have your own training set of data which helps you develop the type of AI clients, machine learning clients you want.
Yeah.
So there's some interesting sort of connections to the to what's happening with AI and machine learning with our work in terms of fluid mechanics, and particularly the CFD codes, the numerical codes that we run. We accelerated them maybe sort of 10 or 15 years ago by starting to run our sort of numerical approximations of fluids on gaming cards. And it's those same gaming cards that are now sort of running these massive large language models and changing the face of the planet.
We were originally kind of tricking the car to think, rather than moving, say, a graphic animation across the screen, it was actually solving the fluid mechanics equations.
Of fluid flow.
But then NVIDIA kind of came in and, made graphics card computing, a serious kind of proposition.
NVIDIA started with this language called CUDA that made it much quicker to do scientific computing. And that, in many ways, was the start of the explosion of the huge adoption of that way of using these kind of simple but very fast sort of computers they're very, very good at a certain type of mathematical computation.
And that sped up what we can do, because you can run a huge number of computations very quickly, so look at a large number of designs, or you can look at very complex computations. So rather than just modelling a small part of your jet engine, you can actually compute the whole aircraft and engine and look at the performance altogether.
And as I understand it, one of the things about the Whittle Lab and the new Bennett Innovation Lab, which is named after Peter Bennett, who's very generously funding it, is that you are trying to create ways to be much more flexible about how you actually test out ideas and products. You put everything together. Do you want to explain quickly what that actually means in practice, what you're doing?
So one of the things we're really trying to do with the new Whittle laboratory, that's almost finished, we're sort of moving in next month, and particularly the Bennett Innovation Lab, is, so traditionally aviation has been very siloed, and we've tried to sort of break that down. Often in new problems, you really need knowledge from across different fields. So being able to bring together quickly multidisciplinary teams and allow them to go for a challenge or a mission for sort of 6 months or a year or whatever, but also allow it to fail quickly. And that needs supporting in a certain way that's not quite how we do our traditional research. So there's a sort of quanta of research that it's either 4 years or 3 years for a PhD, or 3 years for a big collaborative project. And so if you have a large amount of funding for one of these 3-year projects or a PhD, you have one question. At the end of the 3 years, you find out if it was a good question or a bad question. That's no good when you're trying to solve a big problem in a 20-year timescale. That's 4 and a bit PhDs. It just doesn't fit. So we need to be able to move faster, have ideas, test them, let them fail, move on.
Yeah, we're going to have this really exciting kind of project space where we'll have teams, but it will also enable students to come and play, really, and try and look at different ideas, rapid prototype things, and test them. So
it's almost like that ghastly cliche word, a sandbox, where everyone can play around with tests and things like that. And in a way, what I find fascinating is what you're trying to do is not just experiment with ideas, but actually experiment with the very methodology behind how you develop ideas. It's a process that you're experimenting with, as well as the actual intellectual concepts.
Yeah,
it's. I think for us that's absolutely vital. It's almost more important to have impact in the near term. Many of the technologies that. So we talked about changing the fuel. We've got many of the architectures of the planes and engines sitting there on the shelf. There isn't a magic bullet. There isn't some science that we have in the background that's not quite finished yet. It's practically getting everything together. And fluid mechanics is always nonlinear, so it's always surprising enough to need to do it for real. And that's the sort of why it's difficult to move forward. So
it's actually not so much about the technology, because that's there. It's about the execution, to use that word that management consultants always like to toss around.
Yeah, some of that I think is true. It's getting that technology to the stage where it can be flying as well. So the other thing that Nick's test facility enables is to move quicker up to what we call sort of representative demonstration of the technology. So you have the sort of the idea in the shower, then you do the test, or a bit of scrap of paper looking at something. Then you do a test that's a simple test a student could quickly do in a few days, and then you go to these high-speed, more serious tests. But Nick is setting up the facility which will enable us to do those high-speed representative tests incredibly quickly.
So we've got this idea. It's called it's a well-known thing called the Valley of Death. So between the sort of PhD level ideas and then these big traditional test houses, there's a sort of void. It's very hard to get from a sort of £100,000 project to a £10 million project.
So if you're a PhD with a brilliant idea about how to save the world, traditionally, you've had your brilliant idea, it's on your paper, in your model, but you can't actually turn it into a project because you might build it yourself.
It can't bridge that gap.
Scaling up is really hard.
And rather than sort of necessarily a few revolutionary ideas, it might be 25% ideas. So we haven't mentioned it yet, but changing the fuel, to do it sustainably, the amount of electricity that it needs is I would say currently intractable. It's of the scale of the electricity used in the rest of the world. So to take aviation from some sort of sustainable fuel made with sustainable electricity on the ground, as it were, you need the electricity that we currently use. So if we halve that, and there's huge advances in massive rollout of sustainable renewable energy, which we have seen over the last decade. So these things are happening. The sort of doublings are happening. That's why we have to be careful. We need to see these scale-ups as real and possible and historically sort of
it's
realistic.
A good point. A lot of being
but it's not
part
easy.
of the solution to reaching net zero for aviation is having a huge excess amount of renewable electricity supply, because that renewable electricity supply would be what you then use to create your electrolyze to make hydrogen, or you're putting together carbon that you take from the atmosphere and put together with hydrogen molecules to make a sustainable e-fuel, which you use. So the energy that you use to create the fuel is going to be huge and expensive. But that means that the amount of energy used on the aircraft becomes more precious. So we feel then our work in terms of reducing the energy use of the aircraft itself becomes even more important because the fuel is more valuable.
So talking about hydrogen, we've got this sort of cold sink. We talk about increasing the temperature. We talk about these sort of special nickel superalloys for the turbine, for example. So we've been focusing on things being hot and making them hotter to make them more efficient. But we've got this fantastic cold sink in this liquid hydrogen tank in the future. So then we can use sort of our undergraduate thermodynamics, and we can actually make the whole engine much more efficient by using that cold sink. And so we've got a lovely project at the moment looking at that. And it's how do you move the heat around the cycle? And it's absolutely wonderful because in the literature, the ways of thinking about it, the low order modeling aren't quite right. They're not quite there. So this problem has forced us to think in a better and clearer way.
So the stuff that the undergraduates are studying with their thermodynamics is actually directly relating to what you're doing at the cutting edge of the science and innovation.
Absolutely.
And we're talking about the Benefit Innovation Lab. What we're doing with the new Whittle is we're bringing people from different disciplines, but also system modelers. So talking about machine learning and AI, that's where that comes in. You don't want to spend 4 years doing the wrong thing. You're modelling, your low order modelling, the sort of, I see it as a sort of traditional Cambridge way of thinking. That's got to be right so that you don't disappear off in the wrong direction for 10 years.
That's fascinating. By the way, I love this idea of breaking down silos because I wrote a book about silo busting a few years ago, and I always think that silos can make bright people behave very stupidly all the time. So it's great to hear you breaking it down. I mean, obviously, being British, you tend to be very modest, but I know the Whittle Lab has won a whole bunch of awards, haven't you, internationally? I mean, you're out there, punching your weight on the global stage against, Americans and Asian universities and other Europeans, aren't you?
I think, that's true. It's probably the institution that's won the most international awards for publications in gas turbines
in our field,
globally.
Yeah. Right. So well, someone who doesn't track the gas turbine publication world that deeply, I didn't know that. But what do you need to help your work grow and expand? I mean, what's the most important thing? Is it government recognition? Is it more publicity? Is it more money? Is it more industry support? What are the critical things to really help support this?
That's a great question. I would say that we have a new lab, so there's the opportunity there to get the teams together. Obviously, we need to draw in the talent and people enthusiastic to solve the problems we have, but I think that will happen. It's always a need for funding. So, more funding will always help, as any academic will tell you. But yeah, I think the support from government is very important as well, to see it as the issue.
At sort of quite a few levels. So we can push the science. We can hopefully improve the way we do things and break down some of these silos and move a bit quicker. But the carrot for industry, because this problem is quite big, needs to kind of be at the bigger level in terms of, so one country can't just change the rules for aerospace. Maybe Europe is big enough to change the rules for aerospace, but maybe Europe isn't even big enough to change the rules for aerospace. So for the companies, and, way out of my comfort zone in terms of thinking about big investments, 20-year investments on very big projects, the companies need to know that the support is going to be there, or the environment is going to be so that's the difficult thing, because to change the plane from a tube and a wing and 2 engines to a boundary layer ingesting plane with a hydrogen engine, that's bigger than one of these multinational companies can do.
It's very difficult.
It's a bigger project than.
And I think the industry alone can't achieve that. And so I'm looking at some of these propulsion systems, and the barrier in some ways is, will the airframer ever want to make these changes it's got to make to the aircraft to implement them? So even if they have a promise of improvement in fuel burn, lower emissions, so the actual development program and so on is so expensive for them, and also such a big risk. So I think these need to have long-term kind of government support as well.
So it's the carrot and the stick is the tricky one.
Well, I must say, I found this absolutely fascinating. Thank you both so much. I mean, I take away sort of 3 key points. One is that there is no magic wand. It's going to require lots of small ones, but we do have the technologies coming through that really could start to create sustainable flying. Secondly, though, it's going to require a lot of collaboration between universities and governments and businesses all working together in imaginative ways, and probably a change in the way that people are actually developing their ideas and turning them into practical products. And I guess a third big thing I take away, which is really the most encouraging, is that it's so easy to read the headlines and think, gosh, the world is a disaster. There's no hope of any of us making a difference. But what you're doing in very practical ways is really contributing to making the world different. And Frank Whittle did that in World War II with the jet engines. And you're now doing the 21st century version of that, hopefully, in collaboration with a whole range of academics and students here at Cambridge and in King's. So thank you both very much indeed. Good luck for all of our sakes. And let's hope we really can have sustainable flying at some point soon.
Thank you.
Thank you.